Well, hello. If this is working properly, we should have video and audio again. This is Honors Physics, Chapter 13. We're starting on the top of page 345. So we're at the top of page 345. We're going to learn about the combined gas law today. Before we do the combined gas law, we're going to first learn something called Boyle's law. Boyle's law. Boyle noticed that there was a relationship between pressure and volume. Boyle noticed that pressure was inversely proportional to volume. In other words, Boyle noticed that if the pressure of something went up, the volume went down. Imagine having a balloon and you grab the balloon and you start squeezing it from the outside. You start pushing inwards on it. Well, you're applying pressure. The pressure you're applying is going up and the balloon will respond by shrinking. You will compress the balloon. So if you increase the pressure, you decrease the volume. Which means that pressure times volume is constant. Which means that pressure 1 times volume 1 has to be the same as pressure 2 times volume 2. In the balloon analogy, before I squeeze the balloon is sitting there at pressure 1 and volume 1. I apply a different pressure, pressure 2, and I will achieve volume 2. This is Boyle's law. Next is somebody called Charles' law. Charles' law. Charles' law, well, Charles noticed that there was a relationship between between volume and temperature. Charles noticed that if the temperature of something increased, its volume increased. Think about hot air. Everyone knows hot air rises, right? The air gets hotter and hotter. The molecules start flying around faster and faster. They're harder to contain. They become bigger in volume. So temperature goes up, volume goes up. This means that the ratio of volume and temperature is going to be constant. This means that volume 1 over temperature 1 would have to be equal to volume 2 over temperature 2. If I have something at some initial volume and some initial temperature, and I change the temperature to some temperature T2, I will achieve some other volume. This is Charles' law. So we have Boyle's law and Charles' law. If you combine Boyle's law and Charles' law, you get the combined gas law. The combined gas law, which is the combination of Charles and Boyle. I like to call that choyles law, which is just a silly name for the combined gas law, combining Boyle and Charles. Ha 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 ha, joke. At any rate, the combined gas law is when we combine these two. So we have pressure 1, volume 1 over temperature 1 equals pressure 2, volume 2 over temperature 2. This is Choyles' law, the combined gas law. In other words, PV over T is constant, which is what we just said previously. The fact that those are constant means that PV equals a constant times T. There's your constant. Another version of that same equation is PV equals NKT. These are the combined gas laws, the ideal gas laws, where NKT is your other constant. So what is this? Well, little n are the number of moles, and if you took chemistry, R is your gas constant, and the value can be looked up in your textbook. N, if you want to use that, is the number of particles. I can't write right now, hold on. Is the number of particles, and I'll figure out how to write it over here. Number of particles, there we go. And K is the Boltzmann constant. Boltzmann constant. And let's go see if we can find those values in your book for you. All right, here's the Boltzmann constant. The Boltzmann constant you can find The constant K is called the Boltzmann constant, and its value is 1.38 times 10 to the minus 23. Right before it shows you the ideal gas law at the bottom of this page, the new constant is abbreviated R, and its value is 8.31. And you got those 2 units there. So we good with that? All right, cool. So we have our ideal gas law. All right, that takes us to, where did I go? That takes us to the page 346 in your book and page 346, example problem 2. A 20-liter sample of argon gas at 273 Kelvin is at atmospheric pressure, 101.3 kilopascals. We would say that was 1 times 10 to the 5 pascals, but they're calling it 100 kilopascals. So same thing. The temperature is lowered to 120 Kelvin and the pressure is increased to 145 kilopascals. We need to find out A, the new volume, B, the number of moles of argon atoms, and C, the mass of a single argon atom given the molar mass of argon. So we want to find how much argon sample do we have. Okay. So scroll down here and let's see. We have volume 1 is 20 liters. Pressure 1 is 101.3. 101.3 kilopascals. We have temperature 1 is 273 Kelvin. Volume 2 is unknown. That's our goal. Temperature 2 is 120 Kelvin. And pressure 2 is 145 kilopascals. Quick note about units. They've given us our pressures in kilopascals and our temperatures in Kelvin. We're going to be playing with ratios, so as long as our units are self-consistent, it doesn't matter that much. But technically speaking, we like pascals and not kilopascals. Okay? All right, so we're trying to find volume 2. Well, guess what? For part A, pressure 1, volume 1 over temperature 1 equals pressure 2, volume 2 over temperature 2. Solve that for volume 2. And you come up with volume 2 would equal pressure 1, volume 1 over temperature 1 times temperature 2 over pressure 2. Plug in all your numbers and you get volume 2. I'm not going to do the calculation here, but you'll get volume 2, and that'll come out in liters because we used liters for our volume here, 20 liters. Quick comment again about units. Technically, we like meters cubed for our unit. We were able to use liters because we're using ratios. So if we wanted, we can convert that to meters cubed at the end. But you got your answer for part A. For part B, they wanted us to determine the number of moles. Well, we can use ideal gas law. PV equals nRT, and they want us to find little n. Number of moles. Okay? Now, you can do this with P1, V1, and T1, or you can do this with P2, V2, and T2. As long as you use all of the 1s or all of the 2s, you're okay, but don't combine them. You can't have pressure 1, volume 1, and temperature 2. So either way you want to set that up, solve for n, and you got the number of moles. Okay? Part C, molar mass. Well, for part C, as it turns out, the mass we're looking for is equal to molar mass times the number of moles. The problem told us, I forget the number now, the problem told us the molar mass was 39.9. So it's going to be 39.9 is the molar mass times whatever we get for n right here, and that gives us the mass of argon. That is how much argon we used, and that'll come out in grams because of the units of our molar mass. And again, we can convert that to kilograms at the end. Okay, so at this point, that puts us at the top of page 347. You guys should do problems 6, 7, and 8. We can talk about them at a future class. I'm going to end this lecture right there. You guys work on those, and if you get through those, continue on with your homework. All right, let's call it.